Okay. All right. So I don't really want to run this as a lecture. It's a seminar, right? So, but what I want to talk about is first, what we should talk about is first this paper by Martin-Löf.
I had those lines. Those are about the review of the.
All right. I write it here, even though everybody knows how to spell the name anyway. So the paper is from '83, so those are the famous Siena lectures. And so that's what we'll start with, see what's going on there. So, so what do you think is the, what's the most important point of that paper? Assuming you've all read it.
So the beginning spends an awful lot of time analyzing what judgments and propositions are and what needs to be given.
Right. Okay.
Trying to distinguish between the two.
Okay. So a judgment versus a proposition. Okay. So what is it between the two?
In some sense, the proposition is the object of the judgment, and it is asserting the proposition.
Okay.
So almost a part and whole, I guess, or subject object.
Okay, well, this is part of the judgment. I agree with that. So whether it's asserting it or not is a little bit of a different question, right? Because he starts with saying one of the judgments is that A is true. And I would certainly agree that that's an assertion of the proposition A. But there's other judgments he discusses which don't assert A. And one of the points is to make those distinctions. So what are some of the other judgments we might make without propositions besides them being true? But they are propositions. Okay.
True with time, T.
Okay. So A true at time T. Okay, so I don't think the paper mentions that, but that's a very important judgment proposition. So from my perspective, if you just talk about A true, that's intuitionist logic. If you talk about A is true at time T, that is intuitionist and temporal logic. Because we talk about time as part of the main judgment we make about the proposition. What are some of the other judgments?
There was something about necessary, A necessary.
Okay, A is necessary. So in which branch of logic would we study that? Modal logic. Okay. So we have temporal logic, we have modal logic, we have intuitionist logic. Where would we study what are the valid propositions? That would be type theory, right? Because we have to quantify what are the valid types. So this is probably mostly type theory judgment. Other things that come to mind? What other judgments about propositions? Okay. False. A is false. Okay. And that's a really interesting one. Because how does Martin-Löf define A is false? Comes in the third part of the A cannot be true. Yeah, it does not have a verification. It cannot be true. So it's different from the statement like A is true. Because the statement A is true, you have explicit evidence for that in forms of proof. But here we'd say A is false, it means it does not have to. So the question is, there is some issue there. So in my opinion, though, and I've played this through various ways, if you're trying to do classical logic, what you get at is that you define truth and falsehood in a way that's mutually recursive. And when you talk about true and falsehood at the same time, and you make them symmetric, and then you get classical logic. If you only talk about truth, then you get intuition. But if you do that, if you talk about both of them at the same time, then you need evidence for the fact that A is false. So refutation is involved. And not just proofs, but also part of the refutation. So if you prove here, you have a refutation here. If you make them symmetric, you'll end up with classical logic. Anything else?
A is known by some fixed agent.
Okay, some agent K knows A. Okay, so that's epistemic logic. We're getting a pretty good subsection of the things here. So now all of these turns out are very, very interesting in computer science. And I spent the better part of my career trying to figure out what they mean in computer science. Okay. So everybody knows about what A true means in computer science, right? It's a very hard isomorphism, we can make proofs of programs, propositions as time, and all these things. So this is just, if you do that, then you get the traditional way to access the constructivity that exists in balanced programming, essentially by doing the proofs of programs that you can run. Okay. So this is kind of the standard way to exhibit that. Now, where does A as a proposition come in? Any thoughts on that?
If it's corresponding well-formed type, it's a well-formed proposition, so something type theoretic, maybe.
Right. So when you talk about whether something has a proof, you also need to talk about whether it's well-formed, or they can be complicated in type theory. When you talk about what the propositions are, you kind of need that. And in fact, I would say that according to Martin-Löf's paper, it is the notion of a proposition has some conceptual priority over the notion of truth. You need to understand what a proposition is. You need to actually understand the truth, and that comes come up first. Now, A true at time T, what would that correspond to? There's not just one answer. Okay, so we can't figure it out. It took me a few years. Yeah.
I mean, you could see something similar in some form of program logic. At some point in the execution, this became true.
Right. So, I think there's essentially two answers to that. So one is to think about the temporal logic for reasoning about the execution of the program, which changes state. So as time evolves, the state changes. So if you want to reason about the program, you need some kind of temporal logic. So that's one answer. There's another answer. You can examine the structure of proofs. And here you can see you can discern the structure in those proofs. It's interesting, computation relevant, just like you examine proofs here. If you do that for here, then it turns out you can get a good explanation of what's called partial evaluation. So partial evaluation is this idea that you run the program for one stage and you don't get an answer when you get a residual program, but you can run on the second stage. And then you can run that second stage program one stage later and you get an answer in the two stages. So you can kind of divide the computation into a linear set of stages. And then, the time. So at the next time A should be true essentially means what returned is a computation, which is the next time we'll compute the answer at type A. Not right now, but the next time. So you can use a Kurohara interpretation of temporal logic to give an explanation for partial evaluation. A is necessary.
Sort of similar thing, like stage computation.
Right, so you can talk about stage computation. It's very hard to see why A necessary should use stage computation though. What does necessity have to do with staging?
Both kind of modalities. True, at T and necessary.
Yeah, they're both modalities, but the fact that the modality by itself doesn't really tell you what the computation should be. So how do we define necessary truth? All possible worlds. Yeah, you're giving the cookie semantics, which is a whole different thing. So we could also say A is true in world W, Okay, so that gives you something else. But necessity, if you don't think about quickly cement, it's hard to find things necessarily true. That would be temporal logic rather than called time. So the way I would define it is something that, let's say A is true, and I make assumption explicit and I don't put anything there. Let's say it depends, it does not depend on any assumptions. Okay? So according to Martin-Löf, that would be categorical truth, right? Not in the sense of categoric theory. And in the sense of true without any assumptions, compared to contingent truth, which might be true under some assumptions. So if these things are true and something else is true. Contingent truth. A categorical truth is something that doesn't depend on assumption. So what can this mean computationally? So if you know the curve how the isomorphism, usually you write something like this. You have x1, a1, xn, an, and then we have a term n which has type A. Right? So it's something like this. So this is your program, this is its type, these are the assumptions that you work under. Okay. And these are like variables that occur in M. So when you say there are no such thing, okay, but what you're saying is that the term M is closed. Program M does not depend on the assumptions. So the notion of A is necessarily true in modal logic. Unless you do it quickly semantic, but if you do it directly by Hilbert-style rules, it would mean that you have a closed term. And then if you play this through and figure out what it actually means computationally, the rule that says something like, if A is true, then box A is true, okay, corresponds to quotation, okay, because what it says is something like, if I have an M which has type A, that means code of M has type box A. So this type box A that internalizes that the necessity actually corresponds to computationally to a coded expression. So that means you have a coded expression you don't evaluate, you can pass around, and eventually you can evaluate that expression. Okay. So, you know, if you've used languages where you have quotations that you can carry them around unevaluated, and you're looking for the logical meaning of it, that's what you find it. Okay, so knowledge is also interesting. So I think this can play an interesting role in computer security and related questions of privacy, because we can talk about what the principles actually know, not just what you compute, but who has access to them as well. Okay, so the thing that is constant here, if you will, is the notion of a proposition. It's the same everywhere. So a proposition is always part of the judgment, but there's something very rich we can do on top of the judgment to talk about what the proposition expresses. Okay, and it's not just necessarily an assertion of a proposition, which is this one, but it could also be the denial of a proposition or stating the proposition is true at some time. Okay, so that's, I think, making that distinction is one of the very important, maybe the most important message there on the paper. Okay, what else is big to talk about? So judgment versus propositions. Okay. What do we do after that? Okay, so if you look at the title, what does it say? The meaning of the logical constant and the justification of the logical laws. So once we make that, how does it help us explain the meaning of propositions? Yeah.
Well, he says that the judgment, like prop, gives you, or his analysis of that provides analysis of what the proposition is. To know that A prop is to know what verify A.
Okay. So we should probably write that down because it's So know that A is a proposition. Needs to know what counts as a verification. Okay. And I do think that this is the most important observation. That to understand the meaning of propositions, you have to understand in which circumstances is it actually true. That is one of the verifications. If you know that, you know the meaning of the proposition. So this is what's often called the verificationist point of view. Okay. So the meaning of the propositions is not given by some kind of external semantics, where you say, oh, my proposition is a formal object, I have some mathematical mapping to some domain, and I look there like a Tarskian style. But I actually just have to understand when I can conclude that it's true. To understand that and understand the meaning of the proposition. It circumscribes it entirely. Okay. Now he contrasts it a little bit with the verificationists of the 1930s, which I didn't fully understand because I haven't read that 1930s literature. Okay, but I think the first approximation, we can call this verification. Now Dummett, which is done the reading of this, also points out what they call the pragmatist point of view. So anybody know what the pragmatist point of view is?
What's the consequence of it?
Right. So now, what counts as a consequence, or maybe immediate consequence. Maybe I'll just say it counts as a proper use. Okay. Okay, so these are the kind of the definitions, and this one is very highlighted in the Martin-Löf paper. So he doesn't really talk about this alternative point of view. One thing I'm not completely sure about, if you're working in type theory, if it predisposes to one or the other. Certainly in logic, we can look at these two and we can see whether they link to the same notions. And I think Dummett's notion of harmony between understanding verificationist and the pragmatist point of view essentially tells us, yes, the logic that we end up with is really the same no matter which point of view you start. If it started as a verificationist trying to understand the meaning of the proposition by counting the verifications, or you can be a pragmatist, how do we use the proposition, how do we use knowledge that we have? And you end up with the same connectors with the same rules. It all fits together. So we don't really have to decide which one of these two we are because they lead to the same point. So we can shift our perspective as we're looking at logic. Okay, so let's see what that actually entails. Okay. So what the verificationist point of view would entail if we take that position. Okay, so the way we think of propositions is being formed by connectives. So let's start with conjunction. Let's say A and B. And to understand what the meaning of A and B is, assuming you understand the meaning of A and B already, you have to explain what counts as a verification. And the verification here is what would a verification actually be?
Started with a verification of A, the verification of B.
Right. It would consist of verification of A and a verification of B. So usually this is written this way. You have to have a verification of A and verification of B. Okay. Now there's an interesting point here, which is that he says to know a proposition, what a proposition means to know what counts as a verification. Why doesn't he say what counts as a proof? This took me a long time to fully appreciate it. Okay, well, keep that in mind. We'll come back to that question later.
Do you mind restating the question?
Okay. So he says here, what counts as a verification of A? Why didn't he simply say, to know what A proposition means, to know what counts as a proof of A? Without a proof by that determining the meaning.
Well, I think he thinks that they have the same meaning. Right?
Well, if they had the same meaning, then he would have said proof here instead of verification.
Well, I mean, he could have said either.
Okay, no, but they're not the same. They're not the same. They're not the same for a very important reason. And the reason is, well, okay, we'll come back in 5 minutes. In 5 minutes to that. But okay, so the verification of A and B consists of a verification of A and a verification of B. And this, in fact, is a rule of proof. So I think that would support your assertion, right? It's the same. Because this is just a rule of proof. Okay, and then we can justify from that how we can use the knowledge of A and B. If we know that A and B is true, how can we use that?
We eliminate to get a verification of A or B.
And we should be able to get a verification of A, so it's called elimination rule, or we can get one of B. Okay, so let's justify this as a consequence of this definition of the meaning of A and B. So why is it okay to say if A and B is true, I'm not to conclude that B is true?
Because A and B is verified, therefore we had to have verified A.
Right. If you have a verification of A and B, you must have a verification of A and B. And therefore, well, we have a verification of A here, so that's okay, because we must have one here, or we can have one here, because also B is true. Okay. We just reason by the fact this is our definition of A and B. From this definition, this one should follow. Okay. Now we can also take the pragmatist point of view. Okay. We can say this is our definition of the consequences of A and B. Okay. So A and B is the thing that you can take a first component of, and you can take the second component of. And now we have to ask, how can we justify this rule? How do we justify that rule?
So if I have a verification of A and B, I could conclude A and I could conclude B. So it's perfectly the case that we need both A and B to have it to A and B.
And I have B, it means I must have had a verification of A and B.
Go the other way around.
Okay.
Elimination day.
Yeah, and having A and B, you don't know whether you have a verification of A and B. Yeah, I think we have conditions, in conditions, I think there's verification. So it's hard to turn around because this is a definition and then see why this would be true. Anyone else want to show that?
Well, so when I say A true, do I interpret that as I can use A? So I don't want to say I have a verification of A. Not in the specific context of this rule, but in general.
Mm-hmm.
So if I can use A and I can use B,
Mm-hmm.
then I can use A and B because those are the uses that I can get out of it. Something like that.
Right, so you can't get any more out of this than A and B are true here. So any use of A and B would be justified because we're reading A and B. But it's the same argument, it's just turned upside down as to what you believe were the things that you started with. But it is harder to think of, at least for me, to think about the verificationist point of view. Okay, so now I want to talk about the differences in proof and verification. So if proof was the same as verification, right, then we'd say, okay, well, in order to get a verification of A, it's enough to get a verification of A and B. Okay. But that's not a good definition of the meaning of A because it would depend on some arbitrary other B that you don't know about. Okay. So looking at all the possible proofs, including this thing, okay, is not good as a definition of the meaning of the logical connectives because the meaning of A would depend on the meaning of some arbitrary other B. Okay.
So does proof then mean formal proof and verification?
No, it has nothing to do with whether it's formal or not. I think the verifications are some subset of all the possible proofs. Okay. So this here, for example, would not be verification of A. Okay. Because as a meaning explanation, it's not valid because it depends on an arbitrary B.
So instead of proof, possibly a canonical proof or
Right.
select proof.
Right. We want at least that the meaning of a proposition depends only on the meaning of its parts. Right? So we don't want to refer to arbitrary other things in the universe that the proposition doesn't depend on. A proof has no such restriction and can refer to many other things, which is another reason that, you know, you wouldn't define the notion of a verification as being a proof because you are always open-ended in an intuitionistic setting what you can use to prove something by making more and more complicated constructions. But a verification, because it explains the meaning of a proposition, should depend only on the constituents. So he doesn't go through that length in his paper. Okay? But if I were to write, you know, lecture 4 of his lecture, or I want to elaborate on the notion, I would say A and B has a verification, if A has a verification, and B has a verification. And here, this would be a different type of rule. It would be a derived rule that's based on this definition. And it would say, well, if we have a verification of A and B, then some way we can get a verification of A, okay, because it must exist. But it's not a rule that defines the meaning of A. So there is a distinction. There has to be a distinction if you want to use verification and an explanation of meaning between a verification and okay. So let's get through this. Now. Okay, so part of the program, I guess, here is to try to build up sort of the whole apparatus of logic by using the minimal kind of assumptions that you can make, the minimal kind of primitive notions that you have. So I think one of the problems with Brouwer's program and also with Tversky's definition of truth, in my opinion, is that Brouwer takes mathematics as primitive, and logic is like a part of that. And so he defines logic as sort of part of mathematics. But in order to do mathematics, we use implication, we use quantification, conjunction. So we already need to know how to reason logically in order to carry out mathematics. Right? To get kind of a circular, again, get a circularity problem, because where do you actually get off the ground, right? And so Martin-Löf says you get off the ground by starting with the proposition. And then later on, you develop the mathematics based on top of the principles that underlie the judgments in the proposition, rather than the other way around. So mathematics arises from introducing rich propositions that talk about things like natural numbers or real numbers or whatever, rather than taking mathematics as being given and now understanding what logic is in that context. Okay, now I forget what exactly I said that. Okay, so now I want to see what else I need to know in order to define sort of the propositions that we're usually used to. And I want to start with as few judgmental things as I need in order to get off the ground. So we need the notion of a proposition and we need the notion of truth, okay, of a proposition. And at some level, we need the notion of a verification because a verification determines what's actually the meaning of a proposition is. So with that, we can explain conjunction, but that's not very much. So the next thing you want to do is we want to introduce the notion of implication, which is a very fundamental notion. So question is, how do we explain when A implies B is true? So we want to, being verificationist, we want to have some kind of a rule that introduces that. We want to see under which circumstances it's true. The problem is that with the mechanism that they have so far, that's very difficult thing to do. Because what we would like to say here is, well, we can put it different ways. Say there's a function, one is A equals B, or we could say there's a proof of B under the assumption that A is true. Those two things essentially come to the same thing. But this notion of an assumption hasn't really entered yet in our universe. So what Martin-Löf does, he introduces the notion of a hypothetical judgment. Okay. So here's how I want to do that. Let's look at a little proof segment. A and B, and C is true. From that you conclude A and B is true. And maybe from that you conclude that B is true. Okay. So that's a little proof here. But is it really a proof? So if it were a proof, then we'd have proved B is true. Okay, but we haven't really done that. Okay. What we've really done is showing that if you assume that A and B and C is true, then by using rules of inference, you can prove that B is true. Okay. So we actually, when we write these figures, we actually deal with these called hypothetical judgments. If you had a proof of that, you can prove that. Does that make sense? So it's implicit in the notation that we use to write out inference rules. In fact, this rule itself here, okay, is a hypothetical judgment. It says if A and B is true, then A is true. Okay? So if we ever have a proof of that, then we can also love that. That's what the rule means, right? If you have a proof of a premise, then you get a conclusion. Okay? So we have hypothetical judgments, and we're using it in a slightly odd way. We said, okay, under the assumption that A is true, we can conclude that B is true. Except that this assumption that A is true is not available to us outside of this. We can only use it to prove B, but not other things. So the way I write this, the way Martin-Löf writes this is just put parentheses around here, but it has some issues. So I'm just going to write this. I call this X, and I know this is X. So this assumption, which I label X, so X is a justification for the assumption that A is true, which is introduced right here. And it's okay to do that because we're reasoning under the hypothesis A. And all these assumptions happen at the level of judgment, not at the level of proposition. So, for example, we can talk about assume that A is false and try to do something from that. There's nothing wrong with that. Sounds good to me. Okay, so there's a little proof here. The notation is somewhat informal, right? It's not a formal definition, but it's a piece of proof here that you can use this assumption outside of it. All right, so is that our definition of implication? And the question, how can we use that A implies B is true? Okay. How do we use that A implies B is true?
Give me a proof that A is true, I can then enable to get proof that B is true.
But we also have a proof that A is true and a proof that B is true. Okay. Okay, how do we justify that? If we know this, okay. If we also know A, how can we justify B? Because that is a B.
Notion of substitution from our introduction. The ellipses up there,
Yeah.
and sometimes give us a way to construct the verification of B from the hypothetical judgment of A.
Right. So we know A implies B is true. According to the meaning, we must have a verification of it. The verification is a hypothetical proof from the assumption that A is true. Now, if we have a proof that A is true, we can plug that in to use of the assumption, and we get a proof that B is true. So that's his reason there. Okay. So it relies on the fact that the notion of a hypothetical judgment is defined by substitution, which means if you have a hypothetical judgment, B is true, B is true, then And if you ever get the proof of A, you can plug that in here to get a proof of B. Hypothetical judgment is defined by substitution. So we use that definition of substitution here. So at this point, we have used very few judgmental techniques, right? We've only used one single judgment, A is true. We didn't bother with A's proposition, and we used the notion of hypothetical judgment. And we have defined conjunction, and we have defined implication from that basis. Now let's think about the notion of verification. Okay. So here, this rule says, so I'm going to use up arrow to say verification. So instead of saying A is true, I'm saying A has a verification. So to have a verification of A and B means to have a verification of A and to have a verification of B. That's how the conjunction is defined.
Is the error replacing true? Or
Yeah,
okay.
I mean, so, but that's just notation.
Okay, yeah. That's
So let's think of, so I don't have to erase it everywhere, let's think of this being, this meaning it has a verification. Okay, so now how do we understand this rule? Okay. So it's not the definition of conjunction, but how do we understand this rule? Okay, before we come back to that, let's think of this one. This one it says to have a verification of A implies B. I have to have a verification of B. Okay. And what about this assumption A? Yeah, we must be able to use a. So I'm going to use down arrow for something we can use. And the reason is because the elimination will work downwards, the introduction will go upwards. So I always construct the verification like this. When I know something, I can use it from it. Okay, so then if you go to this one here, this one says if I can use A and B, then it's okay to use A. So that's the direction of that rule. So if I can use A and B, then I can also use B. Elimination will downwards. Okay, so this is nice because it means that if I construct a proof. Okay, well actually we should finish this first here. So how do I put arrows in this one? So is this one something I can use or something I have to break?
So if you can use A implies B, then you can use B. I'm not sure about A. I think we need a verification for A, but I'm kind of confused about that.
Okay. Conjecture is need verification. All right, so we should think about whether it's true that the meaning of the proposition is composed only of the meaning of the part. Okay. So here this is true because verification A and B consists of verification of A, verification of B. Here I already know this, so then I can know that that's step one, no, that's okay. Here I already know this, I can use it to get something small, so that's fine. Here I'm trying to find the verification of this, which is the verification of B, which is smaller. And in here, I can use A. By working downwards, I only get pieces of A, right? I only extract parts of it. So I get smaller, so that's okay. So in here, I can get pieces of A, but pieces of A also pieces of A implies B. So I'm not leaving this idea that I own the meaning of a compound proposition. It's just composed of the meaning of its parts. Now here, if I can use that, okay, then I know A and B already, so I can use B here. But here, it's okay with because of an constructive verification of A, it just exists. Which also, I'm not leaving the envelope of things that I already want to. So it's okay to require verification. If you wanted to say we can use A here, okay, so that's down there, it wouldn't be unsound, but it would be reasonable. Because generally there are fewer things that verification use. All right.
But is there now also some rule that if I can verify a proposition, then I can use it or something? Can you do this?
Okay, that's an excellent question. Okay. So let's see what happens when we try to prove that A implies A has a verification. Presumably, this would have a verification. Right? All right. Okay, then we have a verification of A under the assumption that you can use A. Construction calls X. Okay. Okay, we can use A. We're trying to build a verification of A. What do we do with that one? Okay, so the obvious thing is to say, well, there's a rule missing. And the rule says, well, if I can use A, that counts as a verification. Some kind of version. Because being able to use A means you know A. And this is just trying to show that you know A. So you should be able to do that. But there's a small problem with this. I don't know if anybody can see that.
I mean, now we get back to the original problem that if I can use A plus B, I can get a verification of A, even though it's dependent on an arbitrary other B. What is the problem?
I don't quite see how to get there because you always work as a relational downwards and introduction upwards. So it's still going to be just up one of those.
Yeah, but so from A down arrow, I can conclude A up arrow, right?
Right.
So from A and B down arrow, I can conclude A up arrow.
It would be down arrow, conclude A and B up arrow.
Well, first A down arrow,
Just A down arrow,
and then A up arrow.
B up arrow. Yeah.
So I don't know whether this is a problem, but if I recall correctly, you did not a problem before that to find a verification of A, even though that depends on an arbitrary other B, which
Right.
has no relation to A.
But it does here because it's something we'll want to use.
Okay.
Which is an arbitrary proof. So in fact, if you want to prove that A and B implies A, okay, which is something we believe in, you need the subproof.
Okay.
So it's okay because something that we know, we're allowed to use that downward. So this proof is actually okay.
Okay.
It's not easy to say itself. Martin-Löf doesn't talk about this at all. But the issue is because he doesn't formalize the notion of verification. But the problem is that if you take this as a definition, then any proof of A and B should, in fact, any verification of A and B should use the introduction rules. But if you're trying to prove something like A and B implies A and B as a verification, the way you do that is you assume A and B. And you can use that now, call that X. Now you have to prove A and B. In fact, you have to find a verification for it. And now you can use that rule that goes down up. So here we have a verification of A and B. And it's not with this rule because it depends on this one here. So we want to make sure that every verification really decomposes the proposition. What we do is we take that that up-down rule. So define a verification of A, this one, and we restrict it essentially for atomic propositions or variable propositions, which we can't break down any further. So when we can break it down, then we have to use that right here. But if you can break it down, you're not allowed to stop at that point. You have to break it down further. All right. Okay, so I believe that this is a good sort of semi-formal description of the notion of verification. And it's okay to use it as a meaning explanation for the connectors because, in fact, you only will ever work this out one of those. but proofs can be arbitrary and complicated. Use lemmas to also look at that. If so, any questions for this?
If there's a up arrow, can you, if there's something to conclude a down arrow? Okay. Leave it somewhere.
Okay, so this is a really good question. So if we had that, then we can lose this up. Because the reason that the thing down there was subformulas of our assumptions what we're trying to prove is because we can only do it down. And this allows us to do something which could be arbitrarily complicated and then use it. So if you had that, you lose the subformula. But it's still a very, very interesting rule to consider because if we had both of these rules in the full generality, then in fact the notion of something we can use and something and the verification would collapse into the notion of truth. So in fact, if you want to show that everything that's true has a verification, okay, then essentially what you have to show is that this rule and this one here, okay, for arbitrary propositions A are admissible. So now if you put our meta-mathematical hat on, we say we're trying to represent the system. That's what you have to establish. And whenever you have a verification A, it's okay to assume and use that. And similarly, whenever we have an assumption A, we can prove that. That's also okay, even though the rule itself is only restricted to cases when we can't prove it. If we have those two things, then we know that the notion of truth and having a verification coincide. Extensionally, in the sense that every proposition that you prove as true also has a verification. But of course, the evidence for those two is very different. You have many more proofs as evidence than the verifications allow. And that's okay, because in mathematics, we're interested in finding many different types of proofs. But verifications just decompose the proposition we're looking at because they're intended to define the meaning of the connectives. It's a much smaller class of things that you want to look at.
I guess related to that question, can you go from introduction to elimination in the detour sense to get A back? Because you have A and B true, A and B up arrow, you can't use elimination once you have something.
Right. That is the same question. Right? Right? If you have a verification of A and B, can you use it? Right? That's what he's asking. Right? And that's exactly what this rule will allow you to do.
Yeah, so I was wondering if there's some subset, like how we restricted it to atomic formula there, and make the up to down make sense of subsequent uses of introduction and elimination.
Okay, I think as soon as you assume this, I'm not sure that there's well, okay, so if you take a detour, if you think about the secret calculus, you know the secret calculus, then this corresponds to cut, and this corresponds to the identity. And essentially, if you restrict this example just to atoms, then you have what's called an atomic cut, the cut of atomic formulas, which is interesting to look at, but I'm not sure that in this picture it actually finds us anything more than really bad about it.
Do we have, I guess, in this calculus a cut elimination theorem? I mean, you said we could imagine this being possible, but do we know it's true?
Yes, it's true. Yeah. So we have that. There's a theorem, and in fact, I think it may not be proven in my paper, but I've proven it elsewhere. That the notion of verification and truth, I mean, every true proposition has a verification. There's a number of ways, different ways to prove that. It's still important for philosophical, so foundational purposes to have the notion of verification to give the needing explanation. I mean, this is something I could try to show you. Because there's some other things you can do here, but I'm not sure that they're much illuminating here. For example, we can try to find disjunction and so on, but you can look it up. And you don't need anything more than find disjunction. We already have everything on the board. So what's happening is that from just the notion of truth and hypothetical judgment, you can find all the connectives. You can find conjunction, implication, disjunction, truth and falsity. They can all be defined from that. So very, very small beginnings, you can actually make very complicated things. And one interesting thing about these connectives and propositions is that you can iterate these. So you can ask, for example, does A imply B imply that A implies C implies B? You can ask such questions. You cannot ask this about hypothetical judgments because you need to be able to form propositions which have these embedded connectives in them in order to form these complicated propositions. And a judgment is just a judgment about a proposition. So it doesn't make sense to nest it because the two things are different things. So to be able to ask complicated statements like this, we need to take the judgmental notion of the hypothetical judgment, and we need to internalize it as a proposition. So we can nest and talk about the combination of these two ideas. And that's the reason we do it. That's why we allow ourselves to form this new kind of proposition. From understanding what a hypothetical proof is, we can now ask complicated questions of this nature, like this. So when you play with different logic and your different notions of judgment, there's always a step that you go through where whatever your judgmental principle is, you now have to, what I call, internalize that into the logic as a connective, so you can nest it. And it turns out you need surprisingly few judgmental constructs in order to get off the ground with that. In fact, so that my work on logical frameworks would say for the logic we've discussed so far, the PFI was pretty much just three. Okay? So one's the notion of truth, one's the notion of hypothetical judgment, and then we also need a general judgment so we can quantify that for every X. And that's in the paper. I don't want to go too far in that direction. So if you want to have generic ways to define logic, logical framework takes the judgmental principles and makes the first class, and then you see what you can build from that. And so very, very few things are required in order to build these, and then also the quantifiers. When you come to these other logic, then you have to re-examine the question every time. What do we need new judgmental principles?
I do have a question. When we were going through the way to go from the verification of state conjunction and derive, so the derived rule, the elimination rule. So I've seen this happen several times, and I was wondering if, unless we knew where to land, we could do that kind of, maybe conjunction is a bad example, but that doesn't seem trivial. But for like conditional, do you think if we didn't know what kind of elimination rule we wanted at the end, could we, ex nihilo derive that from the introduction rule? Or do we need to know, in some sense, the context in which we were trying to recover?
Yeah. So, so there's some work by Schroeder-Heister that examines how to do that. How to take the introduction rule and systematically derive what the initial rules. And you can do this in a mathematical way. For example, it's a little bit unclear for this one, but in this it's fairly simple because you think of this as being inductive definition, and then the elimination rules of the inductive definitions give you this. The problem when if you try to circumscribe the set of all possible introduction rules, so you can see, oh, this always works, if you can pull out, then the next logic you come across will violate that assumption and widen your, you know. So once you start putting the meta mathematical game and you put yourself outside and you start as an object, and then you close it off, then you have kind of you violate this open-endedness of this intuition foundation for mathematics. You can always add new things. The new things that we add might not fit exactly the kind of things we just talked about, but we can still explain them well in the context of what we understand here. In fact, the final remark of this paper, which I think should be controversial, is something like, okay, well, we haven't gotten that far, but that's the definition of convertibility or computability in proof normalization. Has been transposed into genuine semantical explanations which allow you to see this, just as you can see consistency semantically. And this is the point that I intended to teach in these lectures. So he doesn't do any meta mathematical things like prove normalization or anything like that. It's semantically obvious. I'm sorry. Okay. So
I noticed that as well.
yeah. Yeah.
It's consistency. Well, everything is obviously true.
Yeah. So yeah, but maybe you should still check with mathematical means that you have made a mistake somewhere. But okay, times 18:30. Okay, should we take like 5 minute break and think about computation in this context? Okay.
Anybody say anything? Did anybody say anything?
Not in the chat. There's a viewer.
Hello, viewer.
Hi, viewer.
What I didn't get was explain that if you would write the arrow down here, then this rule would become
I think it's because of the asymmetry between these two
Yeah.
transitions.
Yeah, but why doesn't it become strong? It's applicable in more situations. If you have down, you have You arrow don't have down. that rule. That's the one you don't have. Oh, this is the one you don't have.
Yeah, that's
The one
yeah.
over here. This is the one.
But yes, for atomic
Yeah.
composition A,
Only for.
yeah, you go down to up.
Depends on which direction.
From top to down, it's down to up.
So you definitely can't get a true back. You can have a true. Yeah, you
Well,
what is?
you can't go introduce then eliminate. You
Yeah.
can't do detours.
Right, okay.
Just kind of strange.
Yeah, yeah. That's what this is thinking. You show that you can take that and measure the electric or the,
So I guess I thought this logic would include the local reduction. But with the arrows, it won't do that. The other doesn't talk about that. The arrows don't let you do that.
Right.
You can't get those detours.
You're preventing it because everything has to just be proposed itself.
Right. So avoiding the whole process is just force it to be known first.
I scared away into your.
Too bad.
So, you said, that like three judgmental notions of, categorical, hypothetical, or general?
The true.
Truth, hypothetical, and general. And so, I was wondering, so, like a hypothetical seems to correspond to the implication, right?
Right.
Maybe it's more than that, but.
Elimination of disjunction. Elimination of disjunction.
Yeah.
Case picture.
So then implication you think of as internalizing that thing that exists at the level of judgment. Would you say that, like for conjunction, that internalizes like the idea of a pair of judgments? Would you consider that sort of on a different level than the idea of hypothetical judgment?
You could, but you don't need to if you want to iterate hypothetical judgment. Because in a logical framework, you can say this one would be an introduction takes the proof that A is true
Oh, I see.
and the proof that B is true. And gives you a proof that A and B is true. So if you can iterate the hypothetical in this way, then you could also say it's clear proof like that. But that Curry you get that. So if you want to be minimalistic, you would say so you're saying this is hypothetical in the proof of A, and it's also hypothetical in the proof of B, rather than saying it's hypothetical in A. All right. Computation. So, I'm going to get rid of these arrows now. So this rule we don't need, this rule we don't need. Okay, so now we're trying to figure out where the notion of computation arises in this kind of setting. That's because intuitionistic logic is supposed to be connected to computation in some form, whether it has to be somewhere. Okay, and I guess a good place to look is implication, right? Because we already know that a proof of A implies B is supposed to be a function. It's a function where proof of A to a proof of B, so somehow that function is supposed to do something. And then what does this correspond to here? So it would correspond to taking a function from A to B and an argument that type A, and apply that function to this argument to get a a result of type B. And so now, maybe this stuff over here is a little bit too trivial to be interesting. You see that computation arises when an introduction form is met by an elimination form. So that's exactly what the arrows that we put on prevent. Because if you have a proof that looks like this, so it's A, I'm going to write just A, even though we know it should be A true. It's only reason it should be nothing else. And so we have a proof here that's called P, and it's called P. Okay. And that would be introduction X, this would be X. So if you construct a formula and then destruct the formula, that means in terms of the proof, you construct the proof here and then you can destruct the proof here. And those two lead each other is in computation. And the destructive is the constructive. And logically, what it means is part of the checking that our meaning explanation is actually correct. Because the meaning explanation said if you have proof of A implies B is true, then this is how the verification of that is going to be this. And then we have a proof of A, now we can proceed to construct the verification of B, and we can do that if we take this and substitute it up here for the proof of A. So in fact, you can construct from here B, with the proof B, A is true, and we substitute E, this whole thing, for every place where X is used. And we call this a reduction. Okay. And the reduction is in fact a form of a computation, because this thing is a function. It takes a proof of A to a proof of B. We have a proof of A, and we apply that function to get the proof of B. So the reduction rules that arise when you try to verify that the meaning explanation is correct is the thing which actually does the computation. Okay, and then if you want the programming language, we only need to have a notation of proofs. And then once we have a notation for proofs, then you recognize the reduction as computation rules. But even at this level, you can already see we have this D here and then keep it over here. We have this D and we substitute it up here. So this is already a kind of a substitution rule. And for implication, that's just the normal data reduction. Okay, so that would be one place. Let's have another one. Make sure. Yeah, good question. So we have a D, which is A is true, B is true, we get a proof A and B, and then we can get back to proof A. Okay, we convinced ourselves before that A true is justified because we have here the verification. We already have it. So this elimination is justified. So we can reduce that to just B. So this whole complicated proof is going to be simplified. So again, this rule of computation, this is going to be here, which is about it here. Here, E, and the end elimination extracts the first component of that pair, which is the proof of A. And when we're writing down proof terms, this is exactly the computation rule that says take the first projection of the pair and get out that element. And then the second elimination rule takes the second component and get its union. Okay, please, this makes sense. So an interesting question you can ask, if you only have these two reductions, can you always go from an arbitrary proof to one that's just a verification? So obviously, this thing is not a verification, because a verification of A, you have an up arrow here. We had we get into trouble here because this has to be non-zero this way, right? But then this rule is incorrect because this would have to be a down arrow. Now that extra version says you have not using it down, you can use it, but only with that extra rule. We have for verification. This thing you will not allow. And this thing over here, we have a better shot. This is already verification, but it's because we are limiting it. So the question you can ask is, by doing these reductions, can we eliminate all of these? So, and mathematically, that would mean that you have proven that everything that's true. Here's verification. Everything that's true, we can prove using these rules. Possibly use an undisciplined way, with up and down arrows not matching, because these are just versions of truth. And then we just apply reduction, reduction, reduction. Eventually, hopefully, we get something with the verification. Okay. Plain is yes, I say no. Okay, so the right answer is depends.
Wait, I've heard the questions of the permutation rules.
Yeah, right. So the question is, which connectors do you actually use? So you have only these two rules. Okay, and you do this one here. Then the answer is yes. You can take any proof and put it into a verification as well as the normal form by doing this. The only question you have to answer, there was this other thing, we had the restriction to this, to the down up rule, we only do common formula, so we have to do something there. If you want that little technical detail, then yes, if you have these connectors, you can always do it. But if you have disjunction and falsehood, you can't always do it. Because, well, we haven't introduced disjunction, but the problem is that if you have something like, here's the disjunction rule. If you, in order to use A or B is true, I'm just write it is true, and you're trying to prove that C is true, then you have to show that under the assumption that A is true, you can prove C is true, and under the assumption that B is true, C is true. And these assumptions exist only, X can only be used here and Y can only be used here. Because here you operate on the, you don't know which of those two things is A or B. So we have to distinguish two cases. A, you have to be able to prove C, and B, you have to be able to prove C, but you can't use this assumption outside. And the introduction rules that define the meaning would be saying A or B is true. A is true. One, but the other possibility is that if B is true. That's another reason for thinking introduction, second one, first one. And so these are verification rules. To get a verification of this, you have to have verification of that, or verification of B. And this is a use rule. If you can use A or B, then you can use this. Actually, let's walk through that. So this is verification, verification. Here. You can use that to make sure our subformula property is still justified. Well, if you use A or B, in this branch we use A, well, that's a subformula of this, that's okay. In this branch we use B, that's also a subformula of alpha. And C is the same, so it's a change. And it's a little hard to justify in this formulation, but if you look at the sequence calculus and make these things more formal, you realize what you construct here is a verification of C. So it's not unsound to have a down arrow here, but it doesn't give you verification. So if you can use A or B and you try to construct a verification of C, then you can do that by proving C under the assumption A and B separately. So now the problem here is that if this is some kind of, let's say implication, and then you have an elimination of that. So if this C is C1 implies C2, and then you have an implication elimination. Then you have C1 implies C2 here, and C1 implies C2 here. But these are verifications, and these are real introduction rules. So you don't have an introduction immediately followed by an elimination because you have this intervening rule. And you can't apply the reduction directly because you have this extra order. So that means that these simple reduction rules aren't going to be enough to get you from an arbitrary proof to verification. You need to have more rules in there. And those additional rules are computationally hard to testify.
No, so when we say that A or B is true, the only way that we could have verified this is if at least one of those were true. At least A or B would be true. Right? So there should be some way to get rid of if you're trying to find a verification for C, you just check which side of which disjunct is actually true, and then you substitute in the proof for C from that one.
Okay, that's true unless this is an assumption. Okay. So in the context of a proof, something like A or B implies B or A, then you assume A or B, and you call that X. And then you use OR elimination for that. So at that point, it's an assumption. So you don't directly have A or B sitting out there. So you won't be able to eliminate it from the outside in. And then you somehow need to get inside of that C. So from a programming perspective, what this means is that this kind of situation where this is an assumption happens when you try to evaluate something that's not closed, that has some free variables, which are some assumptions. In programming language, you don't do that. When you run the program, you make sure that you have all the information about the program. So this is a distinction between running a program and trying to take a proof and put it into some kind of normal office for verification. Because the verifications, you can ask for the proof of the verification, even if it's a proof under hypotheses, but you don't usually ask if you can run a program when you haven't completely written it. Okay. Because when you try to run it, it'll get stuck when you call the function that you haven't written yet. But for a proof, it's completely normal to say, to work under the assumption that A or B is true, and now let's see what we can do from that. We don't actually have to run it. So if the reductions are the basis for an operation semantics, we are careful to apply them only if we know that the thing that we're trying to evaluate is actually closed. Otherwise, people won't. But the observation is still very important because if we're trying to figure out for this junction what's the operation, we would try to play the same thing, same rule we apply here. We said, why is this rule justified? Okay. So this is our definition of A or B, that these two rules define it, and now we don't care about the arrows. Okay. Why is it okay to proceed by cases? And the reason is because if you have a verification of A or B, this is how you usually present why these eliminations are specified, right? It has to be either one of A or B. If it happens to be a verification of A, then it can substitute this here. And if it happens to be a verification of B, then we can substitute it here. So in both cases, no matter which of these two rules we apply, we can find our justification. So computationally, it's essentially a case expression. It's a case over some type. Okay, so let's come back to this notion of harmony because it's closely related. So I don't think it's not a regular statement. The idea is that the introduction and elimination rules must be in harmony in a logical sense. So what that means is that, well, from the verificationist perspective that the elimination rules were justified in terms of the induction rule. And if you want to check that, what you have to do is to make sure that no matter how you introduce certain connective, no matter which introduction rule you use, if you follow it by an elimination rule of the same connective, then there already exists evidence for the judgment that you conclude. And if you do this constructively, you don't say just there exists evidence, but we can actually construct it. Constructing this evidence is a notional computation. So you always have to check any combination of introduction rules followed by elimination. So here's one introduction rule. And this is one possibility for elimination. And indeed, the evidence for it already exists. And here's the construction of it. This is the reduction that constructs it. So that's what we have in this case. And then the other possibility is to use the second elimination rule, in which case we reduce it to that. And so this is a second reduction. And so if we check all the those possibilities, we would say, okay, the introduction elimination rules are harmony in the sense that the introduction rules do not let us conclude anything that is not true. They're not too strong. If they were too strong, you might be able to extract something that's not actually true. But we can't do that because anything you can extract by elimination rule is justified by the definition of the introduction. Okay. And similarly here, so here we have only one introduction rule to check against one elimination rule. So if we construct it in this way, the elimination rule is not too strong because when you apply it, we have a way to construct the verification of B by doing this kind of substitution here. And similarly here, if you have a proof of A here, then you take that proof of A and substitute it in this derivation to get a proof of C. So, and that's what we concluded. So that was okay because we have this other piece of evidence for it. And similarly, so that means if we can check that any introduction followed by an elimination is the same connector, we can actually reduce. We know that the elimination was enough to stop. Okay. So the other part of harmony, though, that's often not talked about is whether you're not too weak. That's also important. So let me go through that. So let's say I define it like this. A and B is true. B is true, and that's my definition of conjunction. And then I'm lazy now that I've done this one. Okay? What goes wrong now? So obviously, the elimination rules, the introduction elimination rules, usually they should no longer be in harmony. Something is wrong, right? Because of the platform of the elimination rules. Now, is it sound? Let's check. Any introduction followed by any elimination would have evidence for the conclusion. Yeah, the elimination will sound because here is none. So why? So what's wrong here?
You cannot reconstruct A and B from an elimination followed by an introduction, starting with A and B.
Right.
Instead of introduction followed by elimination, it's the other way around. So you can't get A and B, the sentence back from elimination followed by introduction, or just the same.
Okay. So in order to check that the elimination rules are strong enough, what we want to check is if we have an arbitrary proof of A and B. Okay. Is there a way to apply the elimination rules to which we can reconstruct the proof of A and B by the introduction? So here we have to check all pairs. For soundness, we check all pairs. Any introduction followed by any elimination doesn't get us new knowledge. So everything's already justified. Here we would have to say there is some way to apply the elimination rules, so from the pieces we can construct it. If we can, then we have sufficient power in the elimination rule to reconstruct the proof. Okay. So if we have both of them, that's how we would do it. And then we would reconstruct it. Okay. Now, what does this have to do computationally? Well, it's actually interesting. So what you do is the following. You take an arbitrary proof of A and B, and you convert it to one, which which looks like this. Okay. So you apply the elimination rules, elimination will be constructed. So this is actually a form of expansion. Okay. And so what this basically says is that, well, okay, so I do it on proof terms. If you have a D, which is a proof of A and B, okay, you can expand this into one that does this. Now, what is this rule here? It's end elimination. It's actually the first projection, because this is a pair of proofs. So you build a pair of proofs, one, the first projection of D, and the second one is the second projection of D. So it's actually, from here to here, this is often called an eta reduction. From here to here, it's an eta expansion. You expand something which has a product type, and you actually make it into a product type projection. So computationally, you never do this. You never take one of these things and expand it. But as an equality, it makes sense. So, because extensionally, when you take the first component of this, you get pi 1 of d. If you take the first component of this, you get pi 1 of d. If you take the second component here, you get pi 2 of d. If you take the second component here, you also get pi 2 of d. You get the same one if you take both projections. So it's an equality that can be justified extensionally. But you can also justify it by saying, this is my verification that my elimination rules are not too weak. Now, it also plays a role in what we talked about before. So, this rule, if you have a use of A, then X constructive verification of A, that rule was problematic if A was some kind of compound proposition. So the question is, for example, if you have a proof of A and B, if you can use A and B and you want the verification of A and B, what do you actually do in this case? Because you're not allowed to use this rule. Because you only want to use this when you can't break things down, because otherwise we never actually end up with a verification. We need this rule to be applied, and it's not. But how do you go from here to here? Okay, well, you do exactly what you do here. Okay, so you take A and B, and you take A and B twice. You can use that to get A, and use that to get B. Right? Now we have to get a verification of A and a verification of B here. And then we construct the verification of A and B. So you go through this exact process right in this spot in the proof in order to get to this one. Now this A here and this B here could still be compound form if you want to iterate now. But essentially you do an induction over the structure of this proposition every time it gets smaller. Here you go from using this rule at some compound proposition to one of these smaller propositions. Okay, so if you want to check the harmony of the rules, introduction followed by eliminations, we have to check two things. So one is that any introduction followed by any elimination only gives us conclusions that are already justified. Instructing that justification is a rule of computation. Secondly, we need to check that for an arbitrary proof of the compound connective, we can construct a Vita verification. The way we do that is we extract by the elimination rules somehow the components so we can actually build a verification. And that shows that the eliminations are not too weak. Like we had when you wrote this without the second elimination rule, it was too weak and this thing was better. So I call these things, the first check I call local soundness, and the second one completeness. And that's from the perspective of the elimination rule. So if you make sure that the eliminations are not too strong, you check that the rules are sound because they're justified by the introduction. We only check it locally because we don't look at the whole proof, we just look at one introduction. And this is a local expansion because you take somewhere a proof of A and B and you expand it into one that follows that ends in an introduction. Okay. So when you design a logical system, what Martin-Löf is telling you, to make sure that the meaning explanation makes sense, is you need to check sounds. That's what the paper. I think he's missing the completeness part. So he didn't talk about that. And I think it's in Dummett's work, though, however, the fact that the elimination rules cannot be known. It's not enough to be sound, but they also have to be complete somehow. There have to be enough of them. And the way you check this is by this kind of expansion.
He calls it stability.
Okay. So I think the reason Martin-Löf is talking about it is because he's mainly interested in computation, and this just turns out to be some notion of equality, not directly related to computation. Questions, remarks?
I guess I had a question that came up once you did the expansion for the arrows. Maybe I missed it, but what's the verificationist perspective on atomic formula? I mean, the meaning of a proposition is method of verification, but we've used atomic formula, but we don't really have canonical or ideas of verification in this context.
Yeah, so an atomic formula is like something you can substitute for those propositions for. It's like a hypothesis in something in a hypothesis and a hypothetical proof is something you can substitute an actual proof for. These atomic formulas, they are things that you can substitute a more complex proposition for. So think of them simply as variables.
But are we going to replace them with constants, or are we going to replace them with like sentences, like actual prime?
Anything we do here, you should be able to substitute arbitrary propositions because the judgments we make are independent of what's in your propositions. You can substitute for concrete ones, like 5 is prime, or abstract ones like A1 and A2, that again have variables in them as well.
But then they will have verificationist meanings and stuff.
Okay, so the verificationist meaning is only about connectives, I think.
That's what I'm getting at. Does it not even touch the atomic formula? Or we're just treating them as variables?
Well, they have a meaning as a variable, distinguished variable, meaning in mathematics, something you can substitute for. But you don't explain its meaning by substitution. You don't explain its meaning by introduction or elimination.
Right.
That's what you but you explain by substitution. Just the notion of a hypothetical proof is explained by substitution for the assumption. The meaning of one of these things is actually one of these things, for example, here. What does A and B here? Well, they stand for arbitrary proposition. Yeah, so this whole enterprise becomes a lot harder when we get to like arithmetic. So right, this language is not present. And analysis is a more complicated. But there are in fact type theories out there. So yes, so we can carry that further. But I think the whole thing of the notion of verification is a lot less clear, I guess, when you get into that. When you try to introduce natural numbers and the numbers. More complex subject. But Martin-Löf goes through it in very specific. So, I mean, the meaning explanation. The theorems about it are not as crisp as they're here.
I think the difficulty once you leave the logical domain is one of the reasons why he wanted to separate himself from the logical positivists who used it only for empirical domains. I think it's kind of really hairy on how you verify empirical statements because you can even classify them in the same kind of structural way. You mentioned that earlier. I think that's one of the major reasons why it's not that.
Yeah.
It's hard to talk about.
There was one thing I didn't understand in this paper, which is
I don't know if anybody, why does it make the notion of proposition depend on the truth of other propositions?
Yeah,
Is there something obvious I missed there? I don't,
there's like it's dependent sort of in a by. You can secretly A finds B, where B depends on A.
Mhm.
I guess it all still makes sense.
So in other words, he's just foreshadowing path theory, is that? Okay. Okay.
Where are we looking?
We're looking at, on page 29, I guess, in the Martin-Löf paper. He says the forms of hypothetical judgment that I shall need are not so many. Many more can be introduced and then needed for other purposes, but what's absolutely necessary for me is to have access to the form on the assumption A1 true or AN is true, A is a proposition. It seems kind of, so what is A is false is suddenly no longer a proposition? No, it seems a little bit a drastic requirement. And I think a pet theory, the way I usually think about this is that, I want to say, with Pfenning, I would just say like this, arrow B is a proposition, A is a proposition, and B is a proposition. So that's somewhat simple. Right? Now, if I want this to be quantified, I am calling it a B proposition. Still, I want A to be a proposition, and B a proposition of X colon A, something like this, right? So if we abstract from the X colon A, then this would be A is true, right? A is true. So I think once you get the 10, that's probably needed. In the context of this paper, it's not.
If you needed it, but it wasn't clear why you needed it.
He said he absolutely needed it.
Yeah.
Right? It wasn't-
You like it, but you need it.
Yeah, this other thing that, you know, I swept this A prop under the rug here because what we usually like to do is work under the presupposition that if you're right, like A is true anywhere, that you immediately somehow have in your back pocket some kind of assumption that A is a proposition, because otherwise it doesn't make sense to write it. And he was very careful to make sure that always, yeah, we need A as a proposition, and we can write A is true. Oh yeah, the one other point I wanted to make. The reason I label these assumptions, and he glosses over the point, but I think it's very important from a computational point of view. The question is, if you have a formula like this, we can ask some questions. For example, how many proofs are there of this proposition?
How many proofs can't you always produce some equal?
Yeah, so there's infinite many proofs. Yeah. Okay, so let's make a better question. How many verifications are there? Two. It should be two, right? We should be able to see which one is which. So you want to construct a verification of that. You need implication induction, and you get an A. Well, if you just put parentheses around that, then it's hard to know. And now we have another A. And then, well, we have an A here. So You know, which one, what is this actually? So I think there is some kind of informality to the notation, which is computationally significant because you need the first and second projection. You need lambda x, lambda y x, and lambda x, lambda y y. And that's when I write these things down, you know, kind of write it like this, and then this would actually be justified either by x or by y, and those are two different proofs of the same thing. In fact, there's no proof theory that I know of that would identify those two, they're almost different. The other reason I like this notation is because indeed, you know, this rule is a justification of that assumption. So you have a justification built into the notation. Trying to think if there was something else in this paper. So we still have a few minutes. Maybe we can just play this through. Some other. Yeah, do you have a question?
Yeah, about the, so if you make the distinction between, judgment A is true and being true, and a little uncertain by the, I don't have to.
Okay, which page is that?
So my printout isn't numbered, but I think it's like a 14. 14th.
Okay, it's where it says, I know that dot 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 is true.
So this is, the page starts, there's absolutely no question.
Right.
But,
Mhm.
yeah, so he says, Brouwer says in consciousness, philosophy, and mathematics that there are no non-experienced truths, basic intuitions tenet. This is puzzling because it's been understood to refer to truthful proposition. Including there are true propositions which truth has not been experienced. That is propositions which can be shown to be true in the future, although they have not been proven to be true now.
Okay. So what exactly is the question?
So why does he not care about describing the logic of things that are true?
So I would say that he is describing a lot of things that are true.
Well, so he's describing a logic of known truth rather than like actually. And you can see that there is such a different notion of that.
I didn't read it quite that way. I would say that there's a distinction between something you might have evidence for eventually, and something you have evidence for already. Both of them can be true. Just because you haven't constructed the proof yet doesn't mean it's not true.
Yeah. Well, so so there's also the issue of what means by can be proved or can be shown to be true in the future. So does it mean that there exists a proof of, or merely that we know what, or merely that it is a proposition and that it is true in some sense. I mean, so you could consider that propositions can be true without the existence.
Right. That he explicitly rejects that notion. Something is only true if you have a proof of it, or you can construct a proof of it. There are no other true propositions. That's a little bit later or earlier. I don't forget exactly where.
But so still you could have a logic where you
I'm not sure I quite understood that.
Well, so, in terms of justifying like the, and interruption rule, I mean, so here we're saying that, okay, we can take, we know A to be true, and we know B to be true, and, from that conclude that we know A and B to be true. But you could take that, you know, A, B, line A and B as saying something like, A, can be proven, B can be proven, therefore, A and B.
I don't know. What do you think? Is the idea of true the same as can be proven?
Well, I would probably disagree with that, but at least he's.
No, I mean, I'm
saying
talking
that.
about him, yeah. Yeah.
Yes, but not restricted to one system. Obviously.
For incomplete, yeah. The only reason I said in some other system was just to make it more explicit. But yeah, so you could have something that means can be proven in some expansive.
Yes, broad pluralistic.
Yeah, because everything is always open-ended. You can never draw the line. That you only need to draw the line when you do metamathematics. So, but he definitely does not believe that there's true statements that you cannot prove. I forget exactly where he said that, but it's definitely in the paper.
Certainly the evidence for judgment is extremely open-ended. If I say judgment is evident, is extremely, I think, flexible with regards to the methods that you just covered. Or what the evidence is that you can demand.
Well, so I guess part of my reason for asking is that I'm curious as to whether this emphasis on judgment is essentially tied to his intuitionistic perspective.
I would say so. Yeah.
So can you regard classical mathematics from your judgmental perspective?
I believe you can, but it requires a very different formulation. I mean, from a judgmental perspective, I think the way to do it is that you take as a primitive not just the notion of truth, but also the notion of falsity. And you also say that they're complementary, essentially. So that violates this whole what we did on the board, because truth is only defined in terms of evidence for the judgment, and no other way. But if you make a symmetry between the notion of truth and falsehood, you do in classical logic, then when you have to go to a falsehood, you lose computation of contents, but then you can do classical mathematics. So you can explain it judgmentally, but at a very high cost. Because you have to have a notion of truth and falsehood right from the start as primitives. I don't think you can do it any other way.
So you just take the dual of all the rules. The notion of stuff is true.
For falsehood, essentially. So I've constructed the system a couple of times. It's never very, never turns out to be very satisfying because you lose computation contents, and that's inherent. When you stay purely propositional, you can still give an operational interpretation using this kind of call CC semantics of classical propositional logic. But it doesn't scale to the first ridiculous. Stops at 5 sentences, and then there's no more constructive meaning to be had. And I think it's simply because truth and falsehood have to be mutually independent on each other.
Philosophically, I think it's kind of, I mean, it's like a minority position to have emphasis on, or to not be truth and falsehood as symmetrical. I mean, he seems to even be talking about truth with natural language sentences, and there the normally you wouldn't think of there being this asymmetry. Just take some natural language proposition, Obama is the president, then you talk about what means that proposition, what does it mean that proposition, you find it with something somewhat similar to what he said, what it means for that to be true, but really what you wind up landing on, or what many people might wind up landing on, is that you know what the true conditions of it are, so you know what it means to be true and what it means for it to be false.
Right. Yeah. So his notion of false is not that notion. His notion of false, which is in the back of the paper, is just saying that something is false if it's unprovable. I don't know the exact page number where that is. Yeah. Yeah, so that's in page 42, so fairly close to the end. So A is false means A is not true, which A is not verifiable, A cannot be verified. So the verification is primary, right? And falsehood is a fully derived notion from that, which is very different from the classical point of view that they're opposite duals. So it defines falsehood in terms of not being verified.
So if you would call that also for
I don't know. Never discussed that particular thing with them, so I don't know. Okay, are there other points of discussion? So just a couple of closing remarks. So you can play this through, and like I said, you need remarkably few mechanisms at the level of judgment to get this to work. So if you want to do modal logic in the sense of necessity, then you need the notion of a categorical judgment. You need to know that something does not depend on any assumption. And that has to be like a primitive. If you want to do modal logic in the cryptic sense, you don't need that, because you can just talk about truth in different worlds, and you can talk about, as a judgment, accessibility between worlds. And you can build up cryptic logic with quantifiers and box and diamond from that without any problem at all. Similarly, if you do temporal logic, you don't need anything more than what we already have. You just need the notion of time, and then use introduction eliminations. So, I mean, for example, you can just simply say something like, trivially, circle A is true at time t if A is true at time t plus 1. And then you get an elimination rule that says, well, if I know circle A is true at time t, A is true at time t plus 1. And these are obviously some complete with respect to each other. And so, and you are off, and you can define, now you can see what reduction means and all those kind of things. So once you have the apparatus available, you can do a lot of different things. And I have gone through many of these. So The corrective semantics is simply something like this. If you want to think about it this way. So, say box A is true at W, if W could be alpha, and A is true at alpha. So, and alpha here is like a primary box introduction rule using alpha. So it means A has to do some arbitrary work that you can use from alpha. You need a new judgment form maybe to reach it. So the truth and the reachable. But otherwise, all the stuff that we do today is nothing new. You just figure out, well, are the illumination was strong enough? I mean, whatever. Just go through and figure these things out. So one of the nice things about logical frameworks is that because the logical frameworks are based on the notion of judgment, and it's an extremely powerful notion, you can define many of these things in terms of that. One place I've been working on recently, which is an interesting place. Maybe at some point I can tell you about this later in the semester, but you want to explain linear logic. So linear logic is the idea that assumptions can be used in ones. It's a really weird. Then you don't need any new judgment. You just stick with truth. The only thing you need to change is this notion of a hypothetical judgment. So normally we're used to writing hypothetical judgments. These are your hypotheses that you're trying to prove. And in the proof of that, you can use the hypothesis often if you want. In fact, we've already done so. In the proof of A and B, you get an A. So what we just say is, okay, we make this slightly differently. We'll make a different turnstile here. And all that we say is that, these things, when you use them in the proof of C, you use them up as you do. And so you can base all of linear logic just on this idea of a linear hypothetical term. And then all the connectors of linear logic, all the stuff that you can do there falls out. All you need to do is just one little change in perspective. And the rest will automatically come from that. So the things that you need to rely on, you think about as philosophy explaining these complicated logic, which have all kinds of properties, and we can express very complicated situations. The stuff that you need to rely on the judgmental level is very, very minimal. For all of intuitionistic logic here, up to this point, you only need hypothetical judgments. If you want to add the quantifiers, you also need general judgments. That's not very much compared to how many connectors there are. To understand all of linear logic, we have essentially twice as many connectors. You only need to understand the notion of a linear hypothetical. That's all you need to understand. So there's very, very little assumed, which is why I think it's a very nice philosophical framework in order to try to build logic. It seems to be extremely robust, sort of, in the sense that I've tackled many problems in this way, and of course I fail sometimes. But most of the time, it's there somehow, you just have to figure out. And most of the time, the pieces are already there. You don't have to make them up. By the way, the computation and limitation of the linear hypothetical judgment is in terms of concurrent computation. So you can build the type theory of that, and essentially, rather than we do here, computation by applying function to argument and their inductions, computation proceeds by exchange of messages between processes. So it's a small change of perspective what computation is, but it's not a radical reinvention of everything. And you get a nice computation limitation of all of the logic. So just to advertise in case you're still here in the fall and you're interested in that, I'm giving you a course on substructural logic and graduate course on substructural logic. We'll talk about computation and limitation of linear and other substructural logic. On the computational and to some extent on the philosophical. Okay, any more questions?
Thank you for
Reading the
guest
stuff
lecturing.
again?
Thank you for guest lecturing.
Oh, sure.